Hi, everyone. Thanks for attending the AQAI workshop. Today, I'll be talking about some of our recent work on Coreset clustering on small quantum computers. So this work addresses current problems in the field of quantum machine learning, namely, how can we use a quantum computer to process classical data sets in the current era of noisy intermediate scale QC. So I'll begin by discussing data models and Coresets in the context of quantum machine learning. To start, I want to discuss the current state of QML algorithms. So the main aspect of QML that I want to focus on is the assumptions that these algorithms make about the data models that they are operating under. Put simply, a data model is the way that training or testing data is input and output to any particular algorithm or ML model. An example from classical machine learning might be some large array of data which is stored in memory and the model has read-write access to it. However, on the quantum side of things, algorithms like Grover's search assume access to a quantum oracle, which we can use to query a quantum database and locate a specific entry. The HHL algorithm for linear systems assumes access to a quantum RAM, which allows for the efficient loading and storing of quantum states corresponding to the solutions of a linear equation. And conceptually, you can think of a QRAM like classical RAM, except that the quantum computer has superposition access to it, meaning that it can access a superposition of states at a single time. And finally, there are a wide range of other QML algorithms. Maybe an example might be quantum amplitude estimation, which represent a distribution of classical data as a quantum state, where the basis vectors represent the classical data and the amplitudes of the basis states correspond to the square root of their probability in the classical distribution. And we can refer to these states as quantum samples or Q samples. And many of these QML algorithms assume efficient access to these Q samples, either through a QRAM or through some preparation circuit as shown here. However, given the constraints of current NISQ devices being limited in terms of both size and depth of circuits which can be reliably run, these models are unlikely to be implemented in the NISQ era. Generally, the internal structure of the oracles used in algorithms like Grover's remains unspecified, and it's likely that they will require very deep circuits. Quantum RAM, on the other hand, is likely to be just as challenging to build as constructing a scalable universal quantum computer. And without a functioning quantum RAM, we can resort to constructing Q samples with a deep circuit like so. However, for general data distributions, the overheads associated with these preparation circuits would likely erase any quantum speedup that we had hoped to achieve. And so, assuming we have access to an n-qubit quantum computer, then for any algorithm that we want to run, we'll be limited to n classical bits of input and n classical bits of output. And this becomes a real issue if we want to analyze a classical data set consisting of thousands or millions of data points. And therefore, without access to efficient oracles or QRAM, we will need to use other methods to overcome the limited input-output bandwidth of today's quantum computers. And so addressing this issue, recent work from Harrow explored the idea of using data reduction to allow for the efficient loading of classical data sets onto NISQ processors. This data reduction can be accomplished with Coresets, which are small weighted subsets of the data that accurately summarize the full data set. And Coresets have received quite a bit of attention in the classical machine learning literature, where even models whose computation scales polynomially can become intractable when faced with data sets with millions or even billions of points. And here we're interested in using these Coresets to fit a computation over a large classical data set onto a small NISQ processor. So given some algorithm for constructing a Coreset, we can test how well it performs by taking some model to solve our problem and training that model on the large data set X and training another copy of the model on just the Coreset. So we take our Coreset and our full data set, we train the model on each, and then we compare their performance according to some cost function for the problem that we're trying to solve. And we say that a Coreset is good if the difference in cost between the models trained over the full data set and the core set only differ by some small factor epsilon. And in this case, we'll call it an epsilon core set. And so far, I haven't said too much in the way of how exactly these core sets are constructed, but in general, there are two different ways this can be accomplished. The first is a non-adaptive or offline algorithm for constructing a core set. And in this case, the classical computer alone uses the full data set to construct the core set. And if this core set is small enough, it can then be loaded onto a quantum computer, and the problem of interest, perhaps maximum likelihood estimation or k-means clustering or max cut, can be solved with the appropriate quantum algorithm. On the other hand, we could also imagine a scheme which uses both classical and quantum computation to construct a core set in an iterative fashion, point by point. And so this would be an adaptive or online core set construction algorithm. And I've shown this here on the right. And some examples of where this paradigm might be useful include Bayesian inference, saddle point optimization for two-player games, and so on. Intuitively, the adaptive methods for core set construction appear more interesting and powerful than the offline core sets, because in this case, the quantum computer is actually utilized during the core set's construction. And indeed, this has been the focus of some of our more recent work. However, I won't say too much more about it during this talk, but I will be happy to talk about it at the end if there's any questions. And so our goal with this work is to use a small NISQ processor to cluster a large data set using offline core sets and the quantum approximate optimization algorithm. So with that introduction, I'll now discuss how we can use core sets to help solve k-means clustering on today's quantum computers. So we can construct core sets to help us solve this clustering problem like we saw earlier. And so we first must construct the core set. However, typically the size of the core set depends on many factors, including like the level of error or probability of success that we desire. However, for this work, since we're interested in fitting these problems onto NISQ processors, we'll actually be fixing the size of the core set beforehand to match the number of qubits that are available in near-term devices. And for this work, for ease of implementation and simplicity, we'll just be focusing on the two-means clustering problem. And so in this case, each point in the core set corresponds to a single qubit. So we'll be considering core sets with sizes from 5 to 20 qubits. So we consider core sets constructed via two separate algorithms. The first is due to Braverman, Feldman, and Lang, who provide an offline algorithm to construct epsilon core sets for k-means clustering. And the second is a more naive construction, which simply randomly samples from the original data set to produce a core set of the desired size. So to give a summary of this process, we might have some data set X designated by the blue points here, and then we can use one of these algorithms to construct a core set shown by the red points. And then we want to see how good this core set is. So we train our machine learning models on both the full data set and the core set, producing two sets of solutions. So clustering on the full data set will give us some solution mu, and then clustering on just the core set will give us another solution mu prime. And we can compare how good this core set does by testing these solutions over the entire data set. So you'll see here the mu solutions, the cost is computed over the entire data set. And similarly for the core set solutions, the cost is computed over the entire data set. And this cost function is just the typical for clustering. It's the sum of squared distances to the closest cluster center. So now I'll discuss how we actually perform the clustering with a quantum algorithm. And note that this clustering can be framed in a combinatorial way. We just want to find the optimal partitioning of our core set data points into two clusters, which corresponds to just finding an optimal bit string. And so we could solve this problem using Grover's algorithm to quadratically speed up a brute force search over all possible bit strings. However, due to the finite precision of NISQ processors, Grover's algorithm is unlikely to be implemented in the near term. So instead, we'll use QAOA to find a good partitioning. And so before we can perform the QAOA, we first need to construct a problem Hamiltonian, which we will optimize under. So we start with the two means objective function, which is the same one that I shown on the last slide. Here, we just have a weighted Coreset. So now the squared distances are weighted by their weights WI. And so we notice that minimizing this cost is equivalent to maximizing the squared distance between the two cluster centers. And here, W+1 and W-1 correspond to the summed weights of the points in the +1 and -1 clusters. And under the constraint of equally sized clusters, this cost reduces to a sum of dot products over pairs of points from each cluster. And in this case, I've assumed equal cluster weights for simplicity. But in more recent work, we also explore the case of unequal cluster weights, which we can do by Taylor expanding the Hamiltonian around a different ratio of cluster weights other than just a 50-50 split. And so now that we have this expression, this can be interpreted as an instance of max cut on a complete weighted graph, where the nodes of this graph are the data points of the Coreset, and the edges connecting them are given by this expression here, are weighted by this expression here. And so once we have our problem framed in terms of max cut, we know what that problem Hamiltonian looks like for QAOA, and we can write it down as such. So now the goal of our problem is to find the eigenstate of this Hamiltonian, which maximizes the energy. So now that we've covered how to perform the clustering, I'll move on to some simulation results which test the performance of the QAOA and Coresets on a variety of real-world data sets. So to test this technique, we gathered a set of 6 commonly used machine learning data sets. And for each of these data sets, we performed two means clustering using the entire data set and a classical clustering model. So in this case, we're just using k-means plus, the typical implementation in the scikit-learn Python package. So we're using the classical model to cluster the entire data set. We're also generating M Coresets, where M just designates the size of the Coreset, via random sampling, and then also solving those Coresets with the classical solution. Similarly, we generate M Coresets with the Braverman algorithm and solve those with k-means plus. And finally, we use those same Braverman Coresets and evaluate them with our quantum solution, so with QAOA. However, for these simulation results, we actually report the quantum solution as a brute force search over all 2 to the m partitions, which corresponds to a Grover search solution, and it serves as a bound on the best possible QAOA performance. And for each of these test cases, the reported cost is again this sum of squared distances, and it's evaluated over the entire data set. So this is true for all 4 of these instances. So here we show simulation results for 2 of these data sets, and for each of these plots, the color of the bars indicates the mode that we used to generate this data. And so the dark green is the full data set evaluated with k-means plus. These lighter green bars are the random Coresets evaluated classically. The light green bars are the Braverman Coresets evaluated classically, and the blue bars are our Braverman Coresets with the QAOA bound. And so comparing the random Coresets with the Braverman Coresets, we see that the Braverman Coresets generally do not outperform the randomly generated Coresets. In fact, sometimes the random Coresets perform better, such as in the epilepsy data set. And it's possible that this is due to our restriction on the size of the Coreset, and so we no longer have strict guarantees on the Coreset's performance. Comparing the classical solutions to the quantum solutions on the same Coresets, we see that the quantum solutions tend to be competitive with the classical solutions for Coresets of equal size, slightly outperforming the classical solution for the m=5 Coresets on the epilepsy data set, and matching the performance for the pulsar data sets. And interestingly, some of the lower order quantum solutions actually outperform the higher order solutions. So for these blue bars here, the x-axis is actually indicating the order of the Taylor expansion that we use to generate the problem Hamiltonian. And you'll see here, so for coresets of size 10, that's indicated by the dots here. So these are coresets of size 10. The lower order Taylor expansion actually has a better clustering than the higher order Taylor expansions. And so this is interesting and seems to indicate that finding a suboptimal eigenstate on the problem Hamiltonian may actually result in a lower cost overall when evaluated over the entire data set. So this is an interesting area of future work. For the synthetic data set that we generated, we see somewhat different results. So this data set consists of 40,000 data vectors, all but 50 of which were drawn from a single Gaussian cluster, and the others are drawn from 10 small distant clusters. And here, the Braverman coreset consistently outperforms the randomly sampled coresets, as we would expect, since this data is structured in a way which makes it unlikely that the random coreset will find the distant clusters, and therefore the corresponding clustering solutions will suffer. And we see that the quantum m=5 coreset bound outperforms the classical solution of the same size. And similarly, for the m=10 coresets, we get better performance. However, we have to go to the infinite order Taylor expansion to see that outperforming. And so these results suggest that non-adaptive coresets may perform better for anomaly detection oriented data sets where there's a large cluster surrounded by small distant clusters. However, this does introduce an additional challenge for QAOA because these data sets will not have the equally weighted clusters. And we started to address this issue in more recent work, where instead of expanding the QAOA Hamiltonian around an equal 50-50 split of the clusters, we instead expand around different imbalances. And so to wrap up, I just want to show some of our results from running this QAOA on an IBM Q processor. So this is at the top here, this is showing the instance of an m=5 coreset. So this is the max cut problem that we need to solve. And then on the right, this is the linear topology of the IBM Q Rome device. And so the problem that we want to solve here is how do we map this complete graph onto this linear topology? And so since this graph is complete in the context of QAOA, that means that there will be an interaction between every pair of qubits in the QAOA circuit. And so without all-to-all connectivity, we will be required to put insert swap gates into our circuit, which is suboptimal because these operations tend to be very noisy. However, we can utilize a swap network introduced by recent work, which allows us to perform all n² operations in linear depth, linear in the number of qubits. And so the circuit shown here is an example of QAOA, which utilizes this swap network. And you'll notice that each layer of this circuit is interacting 2 different qubits, and those qubits alternate as you move through the circuit. And by the time you get to the end, every qubit has interacted with every other qubit once. And so this swap network can greatly reduce the amount of noise in the circuit execution when compared to the standard Qiskit compilation. And I'll show the results of this on the next slide. So this histogram is showing the observed counts obtained from running QAOA with and without the swap network. We ran on the IBM Q Rome processor, and the simulation results here indicate that the optimal bit strings are the 01100 and the 10011 states. And so you see the results of our executions with the network, we are able to identify one of those optimal bit strings. And so we would find the optimal clustering for this m=5 coreset. Without the network, however, our execution succumbs to the effects of noise, and so we would end up choosing a suboptimal clustering. So to summarize, we investigated the performance of two means clustering via QAOA using offline Coresets to reduce the size of the data sets that we need to run on the quantum processors. We found that there are data sets, such as our synthetic data set, where the Coresets work well in practice compared to random sampling. However, we were restricted to small Coreset sizes because of the limited availability of qubits. Also, I want to point out that solving k-means via QAOA is in a regime where we would expect the quantum algorithm to outperform the classical variance because of the all-to-all connected nature of the problem. So this would avoid the efficient methods for classically simulating QAOA via the recent light cone arguments. However, these speedups may not be apparent for such small problem sizes, and future work should focus on scaling up to larger Coresets. Finally, this work only considered offline Coresets, and future and potentially more interesting work might consider how the quantum computer can be used to adaptively generate Coresets point by point, and investigating how these Coresets perform in practice. So with that, I want to thank you all, and I would love to take any questions.